when I add them together, they don't add to zero. Okay? So, total momentum is not conserved. But, if I multiply the top equation by V, and I multiply the bottom equation by A, and I subtract them, I get B P1 minus, looks like, A P2. Derivative, yeah, well, I'm going to write the derivative on the outside here. D by dt. The time derivative of BP1, oops, did I write the BP1 plus AP2 is equal to 0. So, in fact, it is a conservation law. It happens not to be the conservation of P1 plus P2. It has the conservation law of BP1 minus A P2. The first example is a special case of this. It's a special case that B is 1 and A is minus 1, I think. And so it's a special case.
What would those constants be? Those constants be?
You could get constants like this. I'll tell you how you can get constants like this. We'll give an example. Supposing we have two particles. It's a good question. Supposing we have two particles with different masses. M, let's call it x dot squared plus capital M y dot squared. X and y do not correspond now to the direction of space. They correspond to the location along the line of two particles. Okay? Or I could call it x1 and x2, but then I would have to write some more indices. X and y. Just this particle is called x, position of this particle is called y. Now let's add to that the potential energy minus v of x minus y. Okay? Now let me change variables. Oops, there's something missing. What's missing? A half. Let me change variables and get rid of these n's here. Or change variables, or change the definition of the coordinates. Let's call the square root of nx, let's call that q1. It's just a change of how I describe the first particle. Instead of calling it x, I'm going to multiply by the square root of little m and call it q1. It's a little bizarre thing to do that way. Same thing for 2. The square root of big M x of y, excuse me, y equals q2. Why did I choose square root of m? Well, by choosing square root of m here, incidentally, the same thing is true of the time derivatives. q1 dot is square root of m x dot, q2 dot square root. What is this here? M times x dot squared is just q dot squared. Alright, so this here becomes q1 dot squared over 2. It's this one. This one is q2 dot squared over 2. And now let's look what happens to v. Minus v. Now x, let's go back to x and y. What is x? X is q1 divided by the square root of little m. So this becomes a potential energy, which is q1 divided by the square root of little m minus q2 divided by the square root of big M. Okay, this is an example where after a change of coordinates it simplifies the kinetic energy. Simplifies the kinetic energy, but it turns the potential energy into something which contains not q1 minus q2, but q1 over the square root of little m minus q2 over the square root of big M. Supposing I wanted to get it in the form with a plus sign in here. Supposing I wanted to get a plus that these conservation laws are connected with symmetries. And we're going to figure out what those symmetries are, and we're going to have a unified discussion of how conservation laws come about. This was just an example of some conservation laws, and we'll work out some more, but at the moment, these are just sort of ad hoc, arbitrary equations we wrote down, and we noticed accidentally that there were some things which were conserved. Alright, that's conservation laws. That's all a conservation law is. D by dt of something is equal to 0.
You're saying that you don't have to have a cyclic coordinate.
Well, there may be cyclic coordinate. There may be hidden in there some other ways of expressing the system so that there really is a cyclic coordinate. That's possible. But it's not to say that there's no way to write the theory so that it has a cyclic coordinate, but it was not written in a way in which there was manifestly a cyclic coordinate. So that's, I think, let's just say there was no obvious cyclic coordinate. And whether there was a hidden cyclic coordinate, it's not important. It's better not to think about it that way. Okay, so let's talk about now the simplest symmetry I can imagine. It's the symmetry of the Lagrangian L equals Q dot squared over Q. Only one Q. That's it. It's of course just a free particle. If Q was called X, we would recognize it as a free particle of mass 1. But what do I mean by a symmetry? I mean by a symmetry a change that you can make in Q, a coordinate change basically in Q, that doesn't affect the Lagrangian. Although you can think of it in two ways. You can think of it actively or passively. You can think of it as a change, a coordinate change that changes the definition of position, or you can think of it as an actual motion. Here's the two ways to think about it. Okay, here's there's an object. Okay. If I put my center of coordinates over here, I would say that that object is at x equals 0. Well, let's not make it so special. It's not at x equals 0. It's at x equals something 1 unit or 2/3 of a unit or whatever. That's the coordinate of that object. I can change the coordinate of that object in two distinct ways, and it really doesn't matter which I do. One way is to change my coordinate system. Now that object is no longer at x equals 1. It hasn't been. But because I've shifted my coordinate frame, the object has changed its coordinate. The other thing I can do is stay at the same place and move the object. They're really the same thing, and we don't really have to distinguish them. But one is called a passive coordinate transformation. That's just moving the center of the coordinates, and the other is called active. It doesn't matter which way we're going to think about it. What we're going to think about is a change in Q, delta Q, which is just some small number. The change in Q is just going to be some small infinitesimal change. So here's our axis. In fact, to begin with, in this case, it doesn't even matter whether it's small. It doesn't even matter whether delta is small. Delta is a number, and this means the change in Q, and all it means is that we either push the particle from wherever it was to wherever it is plus delta, or we change the coordinate frame so that the coordinate of Q is changed by this amount. When we do that, what happens to the change of the velocity? If we change Q in every time, incidentally, when I say we change Q, I mean same shift at all times. Wherever the particle is at any time, we shift it to the right, or we move our coordinate frame back a unit to the left, and change the coordinate in the same way, but always by a fixed amount of delta. Delta could be just a number, 0.001. What happens to Q dot when we do that? Nothing happens to Q dot, because all we've done is add to Q a constant. In other words, we've made a change in coordinates. Q prime is equal to Q plus delta, or minus delta, doesn't matter. We've changed the coordinate from Q to Q plus delta, and because delta is constant, there is also a conservation law associated with this Lagrangian. So at the moment, I'm not yet arguing for the peasant law, and it's the conservation of momentum conjugate to q. With this Lagrangian, p dot is equal to 0. So the canonical momentum conjugate to q is conserved. We're going to link these two things, conservation and symmetry, in a moment. But let's go to the case with two variables, q1 and q2. Where is it? Well, I'll tell you what. Since the first example was a special